So we are starting section 3.2 today. What's unusual, and talking about the empirical rule and z-scores. So we've been talking about distributions, and we've talked about how to discuss the shape. And last video we did the center and spread. And so far, we've only been talking about this for symmetric distributions. And so today we're continuing with symmetric distributions, and wondering what is unusual and where do we expect the data to be. So let's look at the same example we talked about in section 3.1, where we had years, and we had that the mean age was 16 and our standard deviation was 1.58. So now let's talk about what the mean plus one standard deviation looks like. So if we have our mean and we add one standard deviation, we get to 17.6. I'm going to round the standard deviation to be about 1.6. And the mean minus one standard deviation goes to 14.4. Now we're going to look at the mean plus two standard deviations. So we're going to multiply the standard deviation by 2 and add it to the mean. And we're going to multiply the standard deviation by 2 and subtract it from the mean. So there's a dot plot below with our data on it. And now we're going to mark the locations of, being one standard deviation greater than mean and one standard deviation less than. So 17.6 is here, and 14.4 is here. So this area is one standard deviation below and one standard deviation above the mean. So you can see how many data points fall within one standard deviation of the mean. Next, let's put on two standard deviations away from the mean. So 19.2, that's out here, and 12.8. So you can see that all of our data actually falls within two standard deviations of the mean. So the red line marks two standard deviations below the mean, and this is two standard deviations above the mean. So we're going to answer a couple questions about this. How many ages fall within one standard deviation of the mean? So we can actually count up these observations. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 out of our 17 ages fall within one standard deviation. So that's 64.7% of our observations. How many fall within two standard deviations? And we just talked about that. Actually, all of ours do. So that's 17 out of 17 observations, which is 100% of our observations are falling within plus or minus two standard deviations. So oftentimes we'll write that plus or minus two standard deviations. And then finally, it's asking about three standard deviations. And obviously, since all of our data fell within two, 100% is also falling within three. That would even be further out. So plus or minus three standard deviations from the mean. So remember that the standard deviation is the average distance from the mean. Average distance. So some are going to be more than the standard deviation away, one standard deviation. Some are going to be less from mean. Okay. So we have, we're going to introduce the empirical rule here. This is a rough guideline that helps us understand how standard deviation measures variability. So in general, when we're looking carefully at our shape of our distribution and it's unimodal and symmetric, then the following is going to be true, that approximately 68% of our observations are going to be within one standard deviation of the mean. So that's shown on this graph here on the left. We're talking about being between +1 standard deviation and -1 standard deviation from the mean. 95% of our observations will fall within 2 standard deviations of the mean. So again, plus 1 standard deviation greater than the mean, that's this way, or -2, I'm sorry, I meant to say 2 standard deviations away. So 95% of our data fall in this shaded in area here. And the third thing says that nearly all of our observations will be in 3 standard deviations of the mean. That doesn't mean every observation, but almost all observations will be within 3 standard deviations of mean. So how do these compare to what we found in number 1? They're very similar. We had seen 64% were within 1 standard deviation and 100% were within 2 standard deviations. So it's not going to be a perfect fit all the time, but a lot of the time when you have a unimodal symmetric distribution, it'll be a very good fit, the empirical rule. So just to point out here, we're looking at a distribution of heights, and the histogram is the actual distribution of the data. And when we draw this smooth curve, which we tend to do a lot, and we're going to be practicing it ourselves, this is the idealized version of the model. So in general, this is the way the model falls, is that smooth curve. Okay. So the fact that this actual distribution so well fits this idealized model, the empirical rule is going to be a very good fit for this data. Okay, we're going to introduce one more idea today. Just the question kind of got separated from the rest of the work. So we're going to read this question here at number 4. Quantitative SAT scores have a mean of 500 and a standard deviation of 100, while ACT scores have a mean of 21 and a standard deviation of 5. Assume both types of scores have distributions that are unimodal and symmetric. Okay, so we're going to answer some questions about this information on the next page. So just to refresh, so we have it to work with. SAT, it told us the mean was equal to 500, and the standard deviation was equal to 100. So let's just write that up here. For the ACTs, the distribution said that the mean was 21 and the standard deviation was 5. Okay. So they told us that it was a unimodal symmetric distribution. We're going to start seeing more and more of these types of distributions, and when we draw the idealized sketch of them, which we want to do here, we want to kind of draw this neat shape here. So we're going to talk more about it in coming chapters, but it won't hurt us to practice. So if the mean is 500, the peak of our distribution is going to be over 500, and it's going to have this kind of curve to it. And again, over here for the ACTs, we're going to have our peak over 21. And we're going to talk about this type of distribution soon, giving it a name. So let's go ahead and answer these questions. Which of the following is more unusual? A quantitative SAT score of 750 or an ACT score of 28? So let's take a quick peek of where 750 lies. Looks like it's out here. And where 28 is, which is right here. And so kind of you can see what's beyond those two scores. And it's clear that in the SATs, fewer people would be expected to score beyond a 750, whereas it seems more likely we'd see people scoring beyond 28 in the ACT. So the SAT score of 750 seems to be a more unusual score. So that's just kind of taking a quick look at the graph to do that, but we want to be able to quantify that. And so we're going to introduce an extremely important concept to quantify it, and that's called standardizing your scores. So this is a Z-score, and this is going to be a calculation that we're going to be using for the rest of the semester. Pretty much on every test, you are going to be calculating a Z-score. So definitely remember to have this formula with you. So what we have here, I'm going to just rewrite it where I can see it a little better. It got blurred on my overhead. But your Z is your standardized unit, okay, your Z-score. We write Z for that. And that's going to be equal to the value that we're interested in. That's the value that we want to standardize. We subtract the mean. So in other words, we're looking at how far away is our value from the mean, and we standardize it by dividing by our standard deviation. Okay, so how far away is the value from the mean, and divide that value, that distance, by the standard deviation. So let's calculate a Z-score for SATs. So Z, it says if we want to know the Z-score for an SAT of 750, this 750 is our value we're interested in standardizing. How unusual is 750 in this distribution? So we're going to subtract the mean and divide by the standard deviation, and this comes out to be 2.5. Now we can quantify how far or how unusual is an ACT score of 28. So we're going to calculate or standardize this by saying, okay, 28, how far away from the mean is it? And divide it by its standard deviation, which was 5. And this comes out to be 1.4. So, which has the higher Z-score? Our SAT had the higher Z-score, and so that's therefore that's more unusual. That's further away from the mean in its distribution. Okay, so one other idea that you're going to need to be able to do is to go the other direction. If you're given a standardized score, okay, of say negative 1.5, what is the actual SAT score? So we're going to calculate this, but just quickly before we do, I want to think about it. I'm seeing that they're asking about negative 1.5. The two z-scores I've so far calculated were both positive, and the values that we looked at, because we'd already drawn them up on our graphs, were both greater than the mean. So if I'm seeing a negative one, being asked about a negative 1.5, I'm expecting the actual score on the SAT test is going to be less than the mean. Okay, so this is actually what Z is equal to. It tells me the student's standardized score is this. So Z equals negative 1.5. So we're going to use a little bit of algebra to figure out what value would give me a z-score of 1.5. So I'm going to multiply both sides by 100 and then add 500 to both sides, and I end up with x equaling 350. So let's just take a quick peek up at the graph I drew. So a z-score of negative 1.5 is corresponding to an SAT score of 350. So that's less than the mean as we expected. Okay, so that's the end of section 3.2. We talked about the empirical rule and calculating z-scores. This is a very important topic, and as I said, z-scores will be with us for the rest of the semester.